All right. Hi, everybody. We are going to start section 6.3, which is going to be the last section that we're going to cover in chapter 6. This is going to take kind of a different turn from what we've been doing. We've been kind of exploring different ways to integrate. We started with some basic formulas. We opened that up with then the U substitution. We did integration by parts. And then more recently, we had that long list of tables. Okay, we are going to be integrating today, but I'm not necessarily teaching you a new strategy for that. I'm just going to show you a different type of integral. Okay, these are called improper integrals. And before we jump into them, we need to do just a short kind of revisiting here of limits, because limits play a role with how you evaluate an improper integral. Okay, so I just want to refresh your memory that back at the beginning of the year when we talked about a limit, we said that in order for a limit to exist, there were actually two requirements. One is it has to be approaching a single number. So if it just feels like, this just keeps growing and growing and growing, and maybe it's approaching infinity, or maybe it's approaching negative infinity. Infinity and negative infinity are not single numbers, so that would definitely be a reason that you would say, okay, this limit does not exist because it's not approaching a single number. The other requirement was that the left and right hand limits have to agree. That's not something that's going to be applying with these problems. And so I think the key here is that with these problems, sometimes these problems are going to be fractions, okay? And you're going to notice that the denominator of your fraction might be growing, okay? So anytime your denominator of your fraction is growing, whether it's approaching positive infinity or negative infinity, I want you to think about what the overall value of that fraction would be approaching. So I'm going to give you an example here. Let's just start with something simple and say I'm going to write the number 1 as a fraction. Okay, and what I'm going to do is I'm going to leave the numerator the same, but I'm going to cause the denominator to grow. Okay, so this next denominator is going to be 2, and then 3. I'm going to make this one 10. I'm going to make this one 1,000. I'll make this one 10,000. And so my question to you is, as you look at these fractions, and you'll notice the denominators are approaching infinity because I'm causing them to grow, grow, grow. How is that impacting what the overall value of these fractions are? Okay, and if I were to even just kind of plot that on a number line here, we'll just say right here's 0, and we'll put 1 right here. Okay, the very first fraction, 1 over 1, obviously that would be right here. The next fraction, as I cause the denominator to grow, now that's at 1/2. Okay, the next one is at 1/3. You can kind of get the sense that, oh, what's happening as the denominator of these fractions grows, it's causing the overall value of the fraction to get closer and closer to 0. Okay, and that's what this is saying right here. Okay, so we're not doing any integrating just yet. I want you to just look at these 3 problems here at the bottom. These are just limit problems. And what this is saying is, as we let the value of b take on larger and larger numbers, okay? That's what this means when this says as b approaches infinity. You're not really going to plug like the infinity symbol in. Okay, that infinity is not really a number. Okay, so you just have to say to yourself that when this is telling you the limit as b approaches infinity, what they're suggesting is, in your head, if you were to plug in a number for b, and then plug in a number larger than that number, and keep plugging in larger and larger and larger numbers for the b, really what you need to be looking for is the denominator of my fraction getting bigger? And if the denominator of your fraction is growing, even if you're plugging in more and more negative numbers, like -1, and then -2, and then -5, the overall value of that fraction is going to approach 0. Okay? So there really isn't a ton of work for that first one for me to show, other than just thinking through like, hey, if this denominator is growing, if the denominator grows, then my answer is 0, okay? So let's look at this next one here, okay? If we were to plug in larger and larger numbers for that denominator. Now be careful here. It's going to cause this fraction to approach 0, but I still have this 3 in front of it, so my answer to this problem would be 3, okay? Okay, now be careful. On the third one, you'll notice that at first it feels like this e is in the numerator, but do you see how the exponent is a negative? Okay, what I'm going to do at the beginning is I'm going to rewrite this problem so that I'm moving this e to the 2b down into the denominator. If you can physically see that that is technically in the denominator, it's going to make this easier on you, because now as you visualize plugging in larger and larger numbers for the b, that is going to make that e that's in the denominator get bigger and bigger and bigger and bigger. So again, what do we have? Oh, as a denominator approaches infinity, the overall value for that fraction is approaching 0, but we still have this -5, so then my answer becomes -5, okay? Okay, so in a nutshell, if a denominator grows, then the overall value of your fraction should be approaching 0. However, if it's a numerator of your fraction that is growing, well, then the overall value of that fraction is going to just keep growing. Whether it's, if you're plugging in more negative numbers or more positive numbers, it'll either grow to positive infinity or negative infinity. Here's an example, kind of like how I demonstrated on the front, only this time I'm going to make the numerators of these grow. So I'm going to put a 1 here, then a 2, then a 3, then a 10, then a 10,000. You can see this is not approaching any specific number. These fractions just keep getting bigger and bigger and bigger and bigger and bigger. So this would be approaching infinity, which would be where I would say, well, then that limit does not exist. Okay, so let's take a look at these problems here at the bottom. We want to be paying attention to, is a denominator growing or is a numerator growing? Well, on this problem, I can see that this is, get rid of that, this b cubed is in the numerator. So if I were to visualize plugging in larger and larger numbers for that b and then cubing it, since it's in the numerator, it's going to be approaching infinity, so my answer to this is technically going to be that that limit does not exist. Okay. Number 2, look at where that b is, because that's where I'm plugging in larger and larger numbers. That square root of b, it's in the numerator. That is going to cause that to be infinity. This is kind of irrelevant. It doesn't matter if there's like another number there. If one aspect of your problem has a numerator that's growing, then your overall answer is going to be does not exist. Okay, now here the b is in the denominator. So that means that part's going to approach 0. My answer is 1. Okay, and on this one, here's another numerator growing, so this is does not exist. Okay, let's see how this looks in an actual problem here, though. Okay, you can see now on this next part here, we actually have an integration problem. But instead of having a distinct number as our lower limit and our upper limit, this is asking us to calculate the area underneath this graph, starting at 1, but then going to the right forever. Okay, something like if you had a graph like this and then you were wanting to like find all this area that goes all the way to the right forever and ever and ever. Here's what you're going to do at the beginning of these problems. We're going to replace the infinity symbol with a b. Okay, and I'm going to go ahead and pull that x squared right on up to the numerator here. Okay, now when you replace that with a b, you immediately, in front of your problem, need to put the notation, the limit as b approaches infinity. Okay, because it was an infinity symbol that we were exchanging the b out for. Okay, now the next step is just going to be the same. And these are all going to be very simple integration problems. Nothing crazy where you're going to have to do integration by parts or that table of formulas. Now what you are going to have to do though is you're going to have to keep copying that limit notation down. So copy that down. And then remember, when we just basic integration, we add 1 to the exponent. So I'm going to make my new exponent -1. I'm going to multiply in front by the reciprocal of -1, which also happens to be -1. I'm not going to put a plus c because this is a definite integral. So I'm going to put the vertical bar with a 1 and a b. Okay, now let's keep going with this. Keep the limit notation for now. Okay, And let's go ahead, just like we normally do, and we're going to plug the b in for the x minus, be careful with this, plug 1 in for the x. So there's a lot of negatives in this, okay? Okay, so in the next step, again with the limit notation, I highly suggest that if you have negative exponents, that you kind of like move these things to the bottom, okay? So in the next step, I'm going to write this negative 1 over b. I'm going to connect these two negatives right here, okay? And honestly, if you move that 1 to the bottom, it's still going to be 1 over 1. Okay, so this is what we have to work with. Okay. Now, if I just gave you this problem as a starting problem, this problem looks like the problems we did on those first couple pages. Now we're just evaluating a limit, and we're saying to ourselves, well, if I plug in larger and larger numbers for that b, where's the b at? Oh, it's in the denominator. If your denominator of your fraction is growing, the overall value of that fraction is going to keep getting closer and closer and closer to 0. So that becomes a 0, which leaves me with my answer of 1. Okay? Okay, we're going to try one more of these, and then we will stop for today, and you'll just have a handful of problems here to try over this. Okay? So we are going to begin with replacing that infinity symbol with a b, and we're immediately putting the limit as b approaches infinity. Okay, this is going to feel like it's really, really similar to the problem that we just did, although I think our lower limit on this is 2, and the other problem it was 1. Okay, I'm going to pull that x squared up to the top. I'm going to keep writing the limit as b approaches infinity. I'm going to go ahead and do the integration, adding 1 to the exponent, multiplying in front by the reciprocal. Okay, again, writing the limit notation, and then I'm going to plug in, like we normally do here. We plug a b in for the x, and then we're going to plug a 2 in for the x. Okay, now here's the step where it's going to make evaluating this limit so much easier. If things have negative exponents on them, drag those down to the denominator so they're placed in a way that you can evaluate the limit much easier. Okay, so you can see how I'm doing this here. I've got negative 1 over b for my first fraction. It's going to change to a plus 1 over 2, or 1/2, for the second fraction. And now I can look at this and say, okay, I'm supposed to imagine plugging in larger and larger numbers for the b. That clearly is in the denominator of my fraction. That's going to cause the overall value for that fraction to be a 0, and then this would only come out to be 1/2. Okay. By the way, if you get a problem, let's just say hypothetically that if you work this out, let's say at the end of the problem you had a b plus 1/2. Okay, and this is where you were, and you were evaluating your limit. Okay, in this example, notice how then, oh, the b's in the numerator. So if you're plugging in larger and larger numbers there, this just keeps growing to infinity. Well, can't have a limit grow to infinity, so your answer for this problem, you would just say, my answer does not exist then. Okay, that's just a hypothetical. That's not the answer to this problem, but that might happen on a problem or so on your homework. Okay, you guys let me know if you have questions. I miss all of you. All right.